Dear students, welcome. In this video, we are going to talk about the pouring and solidification. Out of this, we will talk about the pouring. So for the solidification, we will make a separate video. We will discuss the pouring here. So basically, the pouring system is nothing but we are going to understand about the gating system in the casting. So here we are going to talk about the gating system. So gating system is actually what? It is the passage for the molten metal starting from to the ladle, molten metal into the ladle up to the mold cavity, through which it passes from each and every parameters into that mold cavity is nothing but the gating system. Means the flow of molten material taking from the ladle up to the mold cavity, whatever the parts or parameters that or via the molten metal is flowing into the mold cavity is nothing but the gating system. Now, which are the parts of the gating system? So basically there are four parts of the gating system. The parts of gating system. If I show you the diagram, say this is a liquid molten metal. Okay. Now see here, if you look at this gating system, starting from the ladle, say from the ladle we have poured the molten metal and it is going to reach into this mold cavity. So the various parts into this mold box, say the molten metal first come here, then it will flow through this passage, ultimately it is coming to the mold cavity. So see here, so this thing is known as the basin, or you can say it is a cup. Then this part is a sprue. This is the runner, and this is the ingot, or you can simply call it as gate. And this is our mold cavity. This is I shown here the riser also. So see here, there are four basic parts that we are considering as a part of the gating system, as this is the cup, then this is the sprue, this horizontal is a runner, and the actual point from where the molten metal get enter into the mold cavity is known as the ingot. So what are the basic parts of the gating system? So we can write it as number one, the basin or cup. Then we are having the sprue, then the runner, and the ingot. We will talk about the riser separately. Okay. Now, please, we will discuss this afterward. But before going into the details about the gating system, we should understand first what are the characteristics for the gating system to be the good gating system. Okay, so the next part from this we will list out various characteristics for the good gating system. Now basically the good gating system always ensures the distribution of the molten metal with the minimum temperature loss, with the less turbulence, and with the less dross or slack. That is, the pure material good should enter into the mold cavity. Now let us see what are the characteristics of the gating system. Characteristics of the gating system. What are the characteristics? So for a gating system, the filling time or the pouring time for the molten metal into the cavity should be as minimum as possible. Number one characteristic is what? The pouring time or the filling time should be as minimum as possible. Pouring or filling time should be as minimum as possible. Okay, so within a less time we have to pour the mold cavity so that the molten metal can reach to the each and every corner in the mold cavity, and equally the solidification will start from the various regions in the mold. Okay, so the next is that no part in the mold cavity should start solidifying before completely filling of the mold. It is not like that half of the portion of mold has filled and start solidification and still we are pouring the molten metal. So there is no such a situation occur in the getting system that the some part of the mold cavity gets started solidifying before completely filling of the mold. So this is the second important characteristic. Third thing is that the velocity of molten metal should always ensures the laminar flow. Okay, so molten metal should be flow into the mold cavity with the laminar flow. Turbulence must be absent. Turbulence should not be there. If the turbulence is there, then there will be formation of the slag, there will be the entrapment of the air, so that will lead to the gaseous defect. So very importantly, the material should flow into the mold cavity very slowly with the laminar flow. Turbulence is not at all accepted. Fourth thing, that the flow must be continuous. Partial flows are not allowed. Partial flows are not allowed. Again the same, if you are partially pouring the molten metal into the getting system or mold cavity, so there are very huge chances of having the air entrapment, and that will lead to the air aspiration. That's why the flow should be continuous. Now if you look at the next characteristic, the only pure molten metal should enter into mold cavity. Okay, so what are the necessary measures you have to take for separating the slag, impurities, heavier impurities, lighter impurities? It should be keep outside from the mold cavity. Only pure molten metal should enter into the mold cavity. That is the next characteristics of the getting system. If we talk about the sixth characteristic, the design of the getting system must be economical and easy to implement. Please remember, you should design the getting system such that there is a less cost, or it should be economical, and the implementation of the getting system can be easy. That is, after casting, it should be broken very easily to take out the casting. So the getting design must be economical and easy to implement. So that is very important thing. Next, very important characteristic that I am going to write here, the aspiration effect should be absent. The aspiration aspiration effect should be absent. We'll talk about the aspiration effect later on, but very important, aspiration means the inhalation. The air will come into the mold cavity and get entrapped, and because of that the gaseous defect may get formed into the casting, and the casting is defective. So the air aspiration should be absent. That is a very, very important characteristic we have to focus on to get the proper and good getting system. And the last characteristic that I want to mention here, I will write on the top. We should select the getting system in such a fashion that there is always increase in the casting yield. Okay, so we should go for such a getting system so that our casting yield, rather in another simple word I can tell, this is the productivity. The casting yield or productivity must be improved. So what is meant by casting yield here? So here this weight of the casting divided by the weight of the molten metal, which have poured into the casting cavity into 100. Basically it is depend upon the type of material you are taking for the casting, which kind of getting system that you have used. But see, casting yield, so once the casting is done, when you break the mold, so you should cut all these getting system, fins, projection, only the casted part you have to take, and you have to weight that part divided by how much molten metal you have supplied in kilograms. Okay, so this is in kg, this is in kg. That will leads to give you the casting yield, and our getting system should be such that our casting yield should be increased and maximum. So these are the 7-8 good characteristics of the good getting system I have mentioned. Please remember, many times the liner questions in GATE, they have asked for 2 marks on this topic. Okay, now we will see the next point, that is the classification of getting system. The classification of getting system. So the getting system can be classified as number A, based on the position of the gates or ingates. These are, we are having top getting, then the bottom getting, then we are having parting getting, and stepped getting system. Okay, so these are the classification based upon where your gate is positioned, whether it is at top, at bottom, at parting portion, or in the horizontal plane or parting plane, or the number of gates, that is stepped getting system. And the next classification is based upon the pressure onto the molten metal. These are having the unpressurized getting system, and second, the pressurized getting system. So this is the classification of getting system. We will see it one by one. So let us talk about the top getting. See, when the molten metal is flowing from this basin to sprue and entering from the gate from top to the bottom. Okay, see here molten metal how it is entering. from top to the bottom, then it is known as the top getting system. Understood? So the entry of molten metal here from the ingate from top to the bottom, it is known as the top getting system. Now the thing is that whenever we are using the top getting system, what happened, as the molten metal is falling from the top onto this sand here, the sand mold. So because of this impact caused by this molten metal jet onto this sand, the erosion of the sand will take place. Okay, and when the sand erosion takes place, what happened? The sand particles are coming in contact with the molten metal, and the reaction takes place, and there is a production of the phyllite, which is FeSiO3. And this phyllite is actually get dispersed into the fine particles everywhere into this mold cavity, and this phyllite is very, very hard. And whenever the casting is over and casting is subject to any machining process, so while machining, if the tip of the tool is come in contact with that flake, phyllite flake, then there are chances of having eroding the tool tip also. Okay, so that's why this is not favorable thing. So this is the actually limitation of the top getting system, where there are chances of having the erosion of the mold and result into this phyllite formation. But the very important advantage of the top getting system is that the pouring time or the filling time is very less. It's less. This is the thing. Now, how to calculate this pouring time or filling time? So see here, pouring time, it can be calculated as the volume of casting divided by flow rate of molten metal. So see here, the volume of casting, suppose V, then flow rate is equal to area into velocity, isn't it? So generally, please remember, see here, hence further we are going to give the names for the casting here. See, this is the cup height, HC, this is the sprue height, HS, this is the area at the top of the sprue. Okay, this is a sprue here, and this area is, say, this is 0.1, this is 0.2, and this is 0.3. So here area is A2 and velocity is V2. Here area is A3 and velocity is V3. And whatever the volume of the mold is nothing but the volume of our casting. Okay, so velocity, if we take here, with which the molten metal is entering into the mold cavity, it can be written as, see, the volume divided by area, generally taken at the bottom of the sprue base, A3, into velocity V3. Okay, so this is how we can able to measure the pouring time, say it is in second. Understood? So one more thing comes into picture here about this area. I will write it this area as AC. So AC is nothing but the choke area. The choke area. This is generally, we can say, the minimum of the three areas we are having. Definitely we will discuss bottom of the sprue base, then runner and ingate. So minimum of these AS or AR or AG, ingate. But normally, see, this, what is choke area actually? So the choke area is the area which meters the flow rate. Choke area क्या करता है जनरली, ये फ्लो रेट को कंट्रोल करता है. एंड इट इज having advantage that when we take the bottom of the sprue base as the choke area, so there are advantages of to get the characteristics for the establishment of the flow early in the mold. Okay, so what is the thing we are, or advantage we are getting by selecting bottom sprue base as choke area. So we get the flow characteristics established early in mold. Okay, for just your knowledge, keep it in mind. Otherwise, please remember that this flow rate, in that flow rate, area is A3. By default, we are going to take hence further the area here as A3. So no need to write about the AC choke area. We have taken this A3 as a choke area by default. The reason is this. Okay, so you get the formula for top gating system. How to calculate the pouring time? The volume of the casting divided by A3, that is the bottom sprue base area, into V3, that is velocity with which it is entering into mold cavity. And for V3, what is the head available here? This total head HC plus HS, which is equal to HT. Okay, so velocity V3 you can write it as under root of 2g HT, isn't it? So this is about top gating system. We discuss about the limitation as well as the advantage. So advantage, we will get the very less pouring time to fill the mold, and the limitation is that the sand erosion is there. Next we will talk about the bottom gating system. So students, the next gating system we will talk about is the bottom gating system. Bottom gating system. So what is bottom gating system? See here. Here the molten metal is going to raise into the mold cavity from bottom to the top. See here. Say this is the mold height HM. This is the manometric head available here, H. So this will be the minimum head here, H minus HM. Understood? So the bottom gating system is what? The molten metal is going to raise into the molten metal from bottom to the top. This is called as the bottom gating system. This is the height of the mold. Please remember, this is the mold. This is the mold height HM. This is the total manometric head available for the liquid molten metal H. So this is the maximum head, and this remaining is the minimum head when the molten metal will rise here and say it is touched here. Okay, so in this case, if you see, the basic advantage is that, so sand erosion is definitely come down because there is no direct impact of the molten metal onto this mold surface. So the sand erosion is totally absent. And the one more thing here, that the loose sand molds where the ramming forces used are less, these are the loose sand molds, can be filled very easily. Instead of in this top gating system, there was a limitation that loose sand mold cannot be filled nicely without sand erosion because impact of the molten metal jet. But here we can do that, where you can fill the loose sand mold very easily without sand erosion. But the limitation of this system is that, say the filling time is more than that of the top gating system. Please remember. So here loose sand molds can be can be poured or filled without any sand erosion, okay, but this is the advantage you can say, and limitation is that the pouring time or filling time is maximum compared to top getting system. So this is the bottom getting system. Now in the bottom getting system, how to calculate the pouring time or filling time? So see, in this we can calculate the pouring time is that volume of casting divided by the area at the base of the sprue into V average. See, this V is the volume and this small v is the velocity. Okay, now here we have to go for the average velocity. So average velocity, how to calculate? V average with the maximum head available and with the minimum head available, we should calculate the velocities. Like see, V max plus V mean divided by 2. Tell me what is maximum velocity here with this head h. So V max here under root of 2gh, and V minimum here is how much? See here very less velocity, root 2g h minus hm. First of all, calculate the V average by this, put the value there. You know the bottom of the sprue base and you know the volume of the casting, you can easily calculate the pouring time. Okay, now one thing is that for the same manometric heights, in the top getting system as well as in the bottom getting system, if you compare, then you can do it by your own that, see, the solidification, this pouring time for the bottom getting system is equal to the 2 times the pouring time for top getting system. I hope you can do this. When the same manometric height for the molten metal is available in case of top getting as well as in case of bottom getting. So top getting, say this is the height, okay, so this is the height, manometric height, this is equal to this is your mold height. Okay, so if you do like that, so this V minimum will be how much? 0, isn't it? This V minimum is 0, then what is V average? That is V max upon 2, isn't it? This 2 will get here, and now for the top getting system, this V divided by A3 into V max, isn't it? So definitely pouring time for bottom getting system will be equal to 2 times this is nothing but the pouring time for top getting system, isn't it? Students, please do this. So many times they are asking this question. 2006 IIT Kharagpur asked this theoretical question for 2 mark, that if we are having the same manometric height for the molten metal or manometric heights of the head, what is the relationship between the pouring time for bottom getting system with the pouring time for top getting system. Next, third getting system, we are having the parting getting system. The parting getting system. So this getting system is basically having the advantages of both top gating system as well as bottom gating system. As for top gating system, we are having the minimum pouring time, and for the bottom gating system, we are having no sand erosion. So both of the advantages are here. Okay, you can see here. So here some part of the mold is in the cope box and some part of the mold is in the drag box of the mold. Okay, so this is how, see, this is the parting plane, or this is the horizontal plane which is separating what? The mold cavity into the cope box as well as the mold cavity into the drag box. So see here, for say whatever the mold cavity which is present in the drag, you are filling this mold cavity as a top gating system, whereas the mold cavity which is present into the cope, then this is get filled like the bottom gating system, isn't it? So this is called as the parting gating system. This is called as the parting gating system, isn't it? And here, how to calculate pouring time? So you can have the parts. For this part, there is a pouring time, say for part A, which is in the cope, and this will be calculated as top gating system, plus pouring time for this part B, which is in the cope. Okay, so it will be feel like the bottom gating system. If you add these two, you will get the total filling time required for that mold, isn't it? So this is the parting gating system. So you are having the mold cavity along the horizontal plane, that is the parting plane, some part in the cope and some part in the drag, and one part can be filled as a top gating system, whereas another part can be filled with the bottom gating system. This is known as parting gating system. This is the parting gating system. Understood? And how to calculate pouring time? It will be like this. So the next gating system is the stepped gating system. Stepped gating system. So whenever there are the large castings, we have to fill with the molten metal. So only single gate is not supplying that much required flow rate to this mold cavity. So in that case, we are using the multiple gates so that the overall pouring time will be get reduced. So whenever in the casting there are multiple ingots are used for the molten metal to get enter into the mold cavity, this is known as the stepped gating system. So from the top view, you can see here, this is our casting and this is our gating system. So there are multiple gates we are providing. So see, it is in the horizontal plane I am showing you. So there are multiple gates that are available. So from every gate, molten metal is getting poured or coming into this mold cavity. Okay, so this is actually step gating system, and here we can calculate the pouring time as, see, volume of casting divided by this A3 into V3, maximum velocity into sprue base area, and you have to multiply this flow rate into through how many number of gates the molten metal is entering into the mold cavity, where N is indicating number of ingots. Okay, so of course, see, if you divide this by the N, definitely pouring time is goes down, that is pouring time is decreasing. Okay, so this is the stepped gating system used for the large casting, use the multiple gates to enter the molten metal into the mold cavity, and yes, it is decreasing the pouring or filling time. So in this video we are going to see the left-over classification of the getting system, that is the classification of getting system based upon the pressure acting onto the liquid molten metal. So before that we should know about the getting ratio. So the getting ratio is nothing but the proportions of the circular cross-sectional areas of the sprue, runner and the ingot, and that can be written as the area of the sprue as to area of the runner as to area of the ingot. Depending upon the choke area, now the getting system can be classified into two types. One is non-pressurized getting system and another is pressurized getting system. Non-pressurized getting system, also known as the unpressurized getting system. Okay, now see, a non-pressure getting system having choke at the bottom of the sprue base, having total runner area plus ingot area higher than that of the sprue area. So in this system there is no pressure existing in the metal flow system, and thus it helps to reduce the turbulence. This is particularly useful for the drossy alloys such as aluminum and magnesium, as they are having very high tendency to form the oxides. That's why they are also known as the highly reactive materials. So for highly reactive materials like aluminum and magnesium, this unpressurized getting system is not useful. And in this getting system they have the tapered sprue base well and pouring basins. Now at particular this unpressurized getting system, the getting ratio, as I told you, how to give the getting ratio? Getting ratio is the proportions between the cross-sectional areas of the sprue, then runner and ingot. Okay, for un or non-pressurized getting system, this getting ratio typically used as 1:4:4, or we can use 1:2:2. So in 2009 or 10 they asked about the 1 mark question, theoretical question about the getting ratio. So getting ratio is the relation between the cross sectional areas for sprue, runner and ingot. Okay, now if you look at some disadvantages of this unpressurized getting system, as in the getting ratio you can see the total runner area and the ingot area is bigger or larger than the sprue base area. Therefore a lot of material or the large volume will be blocked into the runner and ingot. Molten metal की जो volume है वो कहाँ block हो जाएगी, because they are simply going to cut after the casting process, isn't it? So definitely the casting yield, as we learned in previous video, what is meant by casting yield? It is kind of productivity of the foundry industry. So because of this kind of getting system, the casting yield definitely goes on decreasing. Then the getting system need to be carefully designed to see that all the parts flow completely by using the molten metal. Otherwise the partially flowed cavity result into the some air aspiration or some gaseous defect. So this is the thing about the unpressurized getting system. Understood? Now the next classification based upon the getting ratio, we are having the pressurized getting system. So in the pressurized getting system, normally the ingot area is the smallest area, thus maintaining the backward pressure throughout the getting system. And because of this back pressure in the getting system, the metal is more turbulent and generally flows full, and thereby can minimize the air aspiration even when the straight sprue is used. So here the ingate area is the smallest area, that's why certain kind of back pressure is always developed onto the molten metal, and that's why because of this back pressure the material having the molten material having the more turbulence, and therefore it is generally flowing fully throughout the mold cavity. Now when the multiple gates are used, this system allows all the gate to fill fully by the molten metal because of this back pressure. So this system provides higher casting yield, definitely because the ingate area is the smallest area, so no any blockage of volume of molten material into that. So definitely the casting is higher than this unpressurized getting system, and because of the turbulence and the associated dross formation, dross means the lighter impurities formed onto the molten metal. This type of getting system is basically not used for the light alloys, but can be advantageously used for the ferrous casting. Now the typical getting ratio for this pressurized getting system, we can have this getting ratio for the pressurized getting system is 1 as to 2 as to 1. You can see the smallest area for the ingate. So these are the two classifications based upon the getting ratio, that is pressurized and non-pressurized getting systems. So students, as you know that the getting system is having the basin or cup, then this is the sprue, this is the horizontal runner, and the ingate, gate or ingate, and of course this is the riser. So these are the parts that are included in the getting system. So let us see, number 1 is basin. So basin or cup basically act as the reservoir of molten metal. So when you pour the molten metal here, so this is get reserved into the basin, and after that the slow and continuous laminar flow will be provided for the molten metal to flow further into the mold cavity via this sprue, runner and ingate into the mold cavity. So basically this basin or sprue reduces the momentum of the molten metal and ultimately the turbulence caused because of this liquid molten metal. So definitely when the turbulence is less, the dross formation or the slag formation, these are nothing but the lighter impurities are less. So basin, so very important, you can easily understand about the basin is what? The reservoir of molten material. This is a reservoir of molten material. Then it reduces momentum of molten material, so that what happen, the dross or slag formation will be less. Also because of this turbulence get minimized, and because of turbulence get minimized, this dross and slag formation come down. And very importantly, you will have the slow and laminar flow further into the getting system, isn't it? So this is the functions of provision of basin. Understood? Now next is the sprue. So this is one more question asked in 2019, okay, about this sprue. So what is sprue basically? So sprue is nothing but it is the connecting passage between the bottom of the basin and the horizontal runner. See, this is the passage. This is the passage which is connecting this bottom of this basin, and this is the runner. And generally the shape of the sprue is what? The tapered one, the tapered with the circular cross section, so that the air aspiration can be neglected. So that is the reason why we are having the tapered sprue. So this is the connecting passage between the bottom of the sprue and the runner. So what is shape of this? It is generally taper with circular cross section, and because of taper, what will happen? The elimination, you can say the elimination of air aspiration. Okay, so this is known as a sprue. Now the third thing is this. We are having the runner. So the runner is basically placed in, see, it is in the horizontal plane, or we can say that horizontal plane is a parting plane. This is, say, this horizontal plane or the parting plane, where the cope and drag of this mold box are getting separated. Okay, so runner is basically placed in this horizontal plane or the parting plane, and it is the connecting passage between the bottom of the sprue base and the ingate. Please remember, here the runner is here and it is connected between this bottom of the sprue and the ingate, and it is generally horizontal, known as the runner. It is the connecting passage between the sprue base and the ingate. And what is the cross section of this runner? The runner cross section is generally the trapezoidal, like this. The cross section of the runner is trapezoidal. Why trapezoidal? Because trapezoidal cross section is having the maximum value of coefficient of discharge. You know that the Q actual is equal to CD into Q theoretical. So CD value for the trapezoidal cross section is maximum. That is why we are using generally trapezoidal cross section. Okay, so this is about the runner. And the last thing that we are having here in the getting system is that the ingate here. This is the ingate. So what is ingate? This is the actual point in the getting system from where the molten metal is going to enter into this mold cavity. This is the actual point from where the molten metal is entering into this mold cavity is known as the ingot. Please remember this. Understood? And the cross section of the ingot is generally same as that of the cross section of the runner. Okay, but the thing is that there is certain offset between the there is always some offset between the axis of the runner and say this axis of the ingot. Please remember this. Say suppose this is the axis of the runner, okay, then there is generally the offset between the axis of the runner, and this is the axis of ingot, and this is axis of runner, and this offset is generally less than is equal to 5 mm. Okay, so there are the two cases can possible. One is when the axis of the runner is above the axis of the ingot, that is in simple fashion you can say the runner is in the cope, and ingot in the drag. This is the first condition or case, and the second case will be the runner will be in the drag and the axis of ingot will be in the cope. So these two cases can be possible. So let us say first case, that is runner is in the cope and ingot in the drag. That is runner axis is above the ingot axis. So basically this kind of condition we are using in case of ferrous materials like steel, cast irons, heavy density materials, or heavy or high density material. Why it is so? When you are having this condition, that is runner in the cope, see here it is runner in the cope and ingot in the drag, that is runner axis above ingot axis. So what happened during the casting of this high density or heavy materials, what happened, the heavy molten material will be at the bottom, whereas whatever the lighter impurities that are present into that molten material of this heavy density material will be collected at the top. So only heavy pure material, molten material will enter into the mold cavity. Please understood. So this condition for heavy or ferrous materials where the lighter impurity gets separated onto the top and heavy, the molten material which is pure, which is coming into the mold cavity. So this is the first condition. Now we are having the second condition is what? The runner is in the drag and ingot in the cope. The second condition, runner in drag and ingot in cope. So say this is the runner axis and this is the ingot axis. This is runner axis. So here now see, the molten metal is going to come into the mold cavity, say from this is the ingot, from here to here, and this is the runner axis. Understood? So basically now you can conclude which kind of material which are suitable for this condition. So definitely the light density materials like aluminum, magnesium, lighter density materials, these are very useful for this condition. Where what happens here? In the case of light or low density material, what will happen? The heavy impurities will be settled down at the bottom. See here, this blue points I am showing this impurities which are heavy into the lighter material, and only this pure liquid molten material will enter into this mold cavity. Understood? So in this case, the heavier impurities will be settled down and the pure molten material will enter into the mold cavity. So like that, the thing is that there is generally offset between the runner axis and the ingate axis. However, the cross section of the runner and cross section of the ingates are generally same. And what is definition of ingate? This is the actual point from which the molten metal is entering into the mold cavity. So these are the 4 important points of the gating system, or these are the 4 important parts of the gating system. Now students, let us see what are the accessories used in the gating system. Okay, so if you look at the gating system, so students, as we can see here, there are certain accessories I have shown here. That is, you can see here is a filter, this is splash core and the skim bobs, and here is the compensation for vena contracta. Okay, so these are generally the accessories used with the gating system. Now see here, this is a basin in which the molten metal first come. Okay, and definitely because of that basin only, the direct impact of this molten metal jet into the mold cavity is avoided, so that we will get the pure material into the mold cavity. This is the basin actually. So when the molten metal is passed from this basin lower down to the sprue, so there is, we are having the filter, or this is also known as the strainer. Okay, which is made up of the ceramic material and which is porous in nature. So from the basin, whatever molten metal is coming down, it get filtered here, and whatever the slag or the dross, the lighter impurities will be get separated, so that the pure molten metal can flow next to this basin, isn't it? So this is the first accessory that we are using, the filter or strainer at the base of the basin. Okay, now when the molten metal again pass through this sprue, it will definitely come down and have the impact of this molten metal onto this runner part, isn't it? So at the entrance of the runner, we have placed the splash core. Again, this is made up of the ceramic material, and because of the using of splash core, what is going to happen? Whatever the impact of molten metal will be caused on this, and there will be no sand. Yes, there will be no sand, so no sand erosion will be there, and again pure molten metal will flow ahead, isn't it? And next is the vena contracta. The compensation for the vena contracta is given, so that as soon as, where it is given, as the runner started, at the beginning of the runner, we are having this compensation for vena contracta. So if it is not there, if compensation is not there for the vena contracta, what will happen? There will be the sudden vacuum creation chances are very high. And if there is a vacuum creation, definitely there are chances of air aspiration, or the air will come or enter into the mold cavity, and it will lead to some gaseous defects. So that's why we have provided here the compensation for vena contracta. Next, as the material move ahead, we are having the skim bobs, or this is also known as skimming. Okay, so these are nothing but the semicircular cuts are cut into the mold cavity, so that there can be the separation of the heavier impurities at the bottom and lighter impurities at the top of this semicircular cut. So these are known as the skim bobs. Okay, so in this way we are ensuring that only the pure material can be go and enter into the mold cavity, because this is the very important designing characteristics that we have seen in the getting system. That is what? There should be the pure molten matter get enter into the mold cavity. Whatever the slag, whatever the dross, any other impurity should be separated out to enter the pure liquid molten matter into the mold cavity. So students, these are the certain accessories which are used in the mold cavity. Thank you.